Okay, the next quantity is special derived quantity is electrical resistance. What do you mean by electrical resistance? The symbol is ohm, right? The symbol of electrical resistance is ohm. Now, what is this electrical resistance? Electrical resistance is nothing but resistance to the flow of electric charges, right? So if an electric charge is flowing from one point to the other, there is some resistance experienced by it in the opposite direction. So that is called as electrical resistance, resistance to the flow of electric charges, right? So electric current, basically electric current there in a circuit. So 1 ohm is given by volt by ampere. Okay, 1 volt is given by what? Volt divided by ampere. Now, there is a voltage drop in a resistor. So, whenever we are, what is voltage? What is voltage? What is volt? Potential difference, right? So, what is potential difference? The strength of the electric field. So if there is resistance, there the strength drastically reduces there, right? So the strength reduces, thereby the resistance is felt, electrical resistance is felt in the circuit. So therefore, what do we say now? We say that there is a voltage drop across the resistor caused by the current flowing in it. So therefore, what are the base units for voltage, children? Base units for voltage? Yesterday we have studied, that is base unit for volt is kg meter square, correct? Then s raised to second raised to minus 3, a raised to minus 1.
Minus 1.
Correct. Then ampere is what? Ampere is electric current, right? So ampere is ampere only. There is no, because electric current is a fundamental quantity. So we do not have any other base quantity. Ampere itself is a base quantity. Okay. So let us derive this. So voltage is what? Kg meter square, s raised to minus 3, a raised to minus 1 divided by ampere. So finally, electric resistance ohm is nothing but what? Kg meter square, s raised to minus 3, a raised to minus 1. If a which is plus 1, if it will go here, it will become a raised to minus 1 into a raised to minus 1. Bases are same, add the powers. A raised to minus 1 minus 1. A raised to minus, correct? So therefore it will be a raised to minus 2. So this is its base unit. Easy? Understood now? Yes or no? Are you taking down?
Yes, ma'am.
With me? All right. Perfect. Perfect, children. Okay. So now, so what is electric resistance? Quickly, can somebody tell me what is electric resistance? Electric resistance? Rudraksh, what is electric resistance, Baba? Rudraksh, what is electric?
Ma'am, can you repeat, ma'am?
Electric resistance is nothing but, suppose the electric current is flowing in one direction. Okay, there is a resistance to the flow of electric current. That is called as electric resistance. There's an opposition force. All right. So therefore, that means whenever an electric resistance is present in the conductor, its voltage decreases abruptly, right? Because why? Voltage is nothing but strength of electric current. So once the resistance is applied, the voltage decreases. And resistance is given by volt per ampere. Okay, volt divided by ampere. Potential difference divided by the electric current. So we know that volt is nothing but potential difference, which is kg meter square s cube a raised to minus 1. Right? Kg meter square per s cube ampere raised to minus 1 divided by electric current is nothing but ampere. Right? Ampere is itself a fundamental quantity. We do not have base units for it. So I write ampere only. Alright, so all these are nothing but base unit. Ampere A itself is its base unit. Right? So therefore, what do? I have voltage divided by ampere. So volt is nothing but kg meter square per second cube ampere raised to minus 1 divided by a raised to 1. Okay. Now what I'll do? I will bring this plus 1 to up. It will become what? A raised to minus 1. So it will be kg meter square s raised to minus 3, a raised to minus 1 into a raised to minus 1. So this is nothing but kg meter square s raised to minus 3, a raised to minus 2. So this is nothing but resistance. The derived base units. Why am I calling it base units? See, if I'm telling about derived units, it is nothing but V by A, voltage by A, that's all. But base units, when I'm mentioning base units, then you have to convert it in terms of the 7 SI units. That is mass in terms of kg, then length in terms of meter, then time in terms of second, right? So that is called as base unit. So we are converting this SI unit into the base units. That's all we are doing. Okay. So once we are thorough with those 7 SI units, what they look like, what are they, and if I know what is voltage, what is ampere, what is its fundamental quantity. Okay, so there, once I know all of this, then easily I can derive the rest. Okay, so make those basic very strong. You have to practice it. You have to go through it. You need to study it. Practice more times. Okay, sometimes it is very difficult for us to remember. So you need to remember what it means. So once you understand, okay, resistance means flow of current. That means the potential decreases. Electric current is present. So V by A. V by A is its formula. So what is its formula? What is velocity? Sorry, potential's formula, right? What is potential's formula? And what is the current? Current is nothing but ampere. So potential is nothing but kg meter square per s cube ampere raised to minus 1. So apply that, divide by A, get the answer. Got it, children? Got it how to do? Yes? No?
Yes, sir.
Yes, ma'am.
All right. Good. Now we will go ahead with the next one. That is conductance. Conductance. What is conductance? Conductance is nothing but the degree to which an object conducts the electricity. Okay, how much the object can conduct the electricity. That is called as conductance. There is some object. Okay, how much can the electricity flow through it? How much does it produce this electric current? So that is called as conductance. Okay, so the unit of conductance is nothing but opposite to that of resistance, right? So unit is nothing but the current which flows through it, current that flows through it, divided by how much is its potential difference or strength of the current. Potential difference or its strength. All right. So what is potential difference? The difference between electric potential between two charges, right? So if this is plus Q and this is plus Q, two charges, how much is its strength? That is nothing but the potential difference or the strength of electric charge, we call it, right? Or volt that we usually symbolize. So conductance is nothing but it is the opposite of resistance. Resistance opposes the flow of current, but conductance conducts it more, right? How much the current can conduct through that object is called as conductance. And the unit of it is current, how much it is flowing divided by its potential difference. So the current that is flowing is nothing but A divided by the potential difference V, right? So A as it is divided by what is the potential difference V, children, in terms of base unit? We know that it is kg meter square per second cube ampere raised to minus 1, right? So therefore A, now let me bring all these quantities up. So it will become A is here already. There is one more A here. So A raised to 1, then A raised to minus 1, if it will go up, it will become A raised to 1 plus 1. Then per kg, because kg is in denominator, if it will go to numerator, it will become per kg. Just like 1 by 2. How will I write it? 2 raised to minus 1. Correct? If it will go up, 2 is raised to 1. Correct? So if this 2 raised to 1 will go in the numerator, it will become 2 raised to minus 1. Just like that, I am deriving this as well. Yeah? So it is per kg. Now meter square is in denominator. If it will go up, it will become per meter square. Correct? Then second minus 3 is there. So per second cube, if it will go up, it will become second raised to cube. Then ampere is already added. So it will be what? A raised to 2 per kg per meter square second. This is nothing but conductance. And how is conductance denoted? Mho. Like this. Ulla. Mho. Okay? This is nothing but the unit of conductance. Clear? Clear with conductance? Yes or no?
Yes, ma'am.
Yes, ma'am.
Everybody, children, I want to see you. I want to say yes, ma'am. Give a thumbs up. Yes?
Yes. Yes, ma'am.
Okay. All right. So it's easy. Now you're understanding what we're trying to do. We are just trying to find the SI unit and how is it in terms of base units. All right. Base units means kg, second, meter, then luminosity, then current ampere. All right. Kelvin when it comes in temperature. All right. Now we'll go ahead with the next one. Next we'll derive magnetic flux. Okay. Magnetic flux. What is magnetic flux? Magnetic flux is the total number of magnetic lines of force in a magnetic field. Suppose this is a magnetic field here. Okay? The total number of magnetic lines of force that are in this magnetic field, that pass through the magnetic field, this is called as flux. So group of magnetic lines of force make magnetic flux. Okay, please take down the definition. The total number of the total number of the total number of the total number of magnetic lines of force, magnetic lines of force in a magnetic field is called as magnetic flux. Okay? Okay? And the unit of magnetic flux is called Weber. Is called as Weber. All right? And the symbol of Weber is WB. Weber. Okay. Now, it is nothing but magnetic flux is denoted by velocity second, volt per second, or it is also nothing but joule per ampere. Joule per ampere. Okay. So what is joule? What is joule? Why do we measure joule? Yes. What is joule, children? Energy, right? The energy experienced by the object when an electric charge flows through it. Nothing but electric current. Oh, sorry. Not electric current, not electric current. I'm talking about work done, right? So energy or work done. Sorry. I'm just confused. Okay. Joule is nothing but the energy that is experienced by the magnetic lines of force when a charge passes through it, when an electric current passes through it. So that is nothing but joule divided by ampere, J by A, right? So this is nothing but what is joule, children? What did we derive for joule? What was for joule? Yesterday we derived for joule kg
kg meter square per
meter
second.
square per second square divided by current is nothing but ampere only, right? Right? So how much work done? That what energy is experienced when current flows through it gives nothing but what magnetic lines of force or magnetic flux, right? So therefore, when we are deriving the base units for this, it is nothing but kg meter square per second square divided by A. So therefore, we can write what kg meter square second square, then divided by A is here. If it will go in the numerator, it will become per ampere. Yes? A raised to minus 1. Clear? Clear with this? Yes?
Yes, ma'am.
Okay. Can I get everyone thumbs up? I want to see everyone thumbs up. If you have understood. Yes or no? Yes or no, children?
Yes, ma'am.
Okay. All right. Okay. What about Piyusha? Piyusha understanding?
Yes, ma'am.
Merrick? Merrick? Understanding, Merrick?
Yes, ma'am.
Okay. Now we'll go ahead with the next one, that is magnetic field or magnetic flux density or magnetic induction. Okay, the next quantity that we will derive is for magnetic field or magnetic flux density, magnetic flux density or magnetic induction. Magnetic induction. All these are same. Okay. Magnetic field or magnetic flux density or magnetic induction. All these quantities give the same base units. All right. So what is magnetic field, children? Yes. When a moving electric charge, suppose this is a conductor, when an electric charge moves in the conductor, there is magnetic field experienced by the object. Correct? So that is nothing but what? Magnetic field. Right? What is magnetic flux density? Magnetic flux density or induction is the number of lines of force passing through a unit area of material. How many magnetic lines are passing in this area? That is nothing but magnetic flux density. Last in the previous derivation we saw what magnetic flux, right? Now the density of the magnetic flux is nothing but magnetic flux density, right? So and it is denoted by Tesla. Tesla. The unit for it is Tesla, not the one which Elon Musk has introduced. This is a different Tesla. This is unit of measuring magnetic field or magnetic lines of force. Okay, and Tesla is nothing but Weber per meter square. Okay, Tesla is nothing but Weber per meter square. Now, what is Weber? Weber, what is Weber? Magnetic flux divided by the area. So how much magnetic flux is experienced in that particular area gives you the magnetic field or magnetic flux density or magnetic induction, right? So therefore, we know that Weber, when we derived previously, was kg meter square second square a raised to minus 1 divided by meter square, right? So this becomes kg plus meter square cancel. So only second square a raised to minus 1. Clear? Clear, children? So this is the derived unit for, derived base quantity for Tesla or Weber per meter square. Clear? Is this clear? Understanding little something? Yes? No? Children, I need.
Yes, ma'am.
Yeah. All right. Perfect.
Clear, ma'am.
Go ahead. Next is inductance. Okay, let's know about inductance. What is inductance? Inductance is nothing but when there's a charge in the current flowing, the electromotive force is generated in the conductor. That is called as inductance. Okay, there's a force that is generated in the conductor when a charge moves. That force of the charge is nothing but inductance. It is inducing something. It is inducing certain energy. That is nothing but inductance, right? Induction, inducing. All right. So when there is a change in current flowing, suppose there's some change when the electric current is flowing, the electromotive force, EMF, right? The electromotive force is generated in the conductor whenever there's a change in the electric current. Suppose some ampere of current is flowing through the conductor, suddenly it changes. So that time EMF is induced, right? So therefore, this is nothing but what this is called as inductance. When an EMF is induced in a change in current, that is called as inductance. All right? And inductance is the SI unit of inductance is Henry. Henry. Okay. And the symbol is nothing but H. Okay. Henry is nothing but Weber per ampere. What is Weber again? What is Weber?
Magnetic flux.
divided by the current flowing through it. Okay, so there's a change in magnetic flux when there's a change in current, right? Divided by the ampere, that means the flow of current. So therefore, Weber per ampere is nothing but inductance. Whenever there is a change in the electric current that is flowing in a conductor, suddenly an electromotive force, there's a force which is induced called as electromotive force. So that force produces inductance. And that is nothing but given by Henry. Okay, Henry's symbol is H. Okay, and Henry is nothing but what? Weber per ampere. What is Weber? The magnetic flux induced divided by ampere, the current flowing through it. So therefore, let us derive what are the base quantities for Weber per ampere. The base quantities are Weber is nothing but, we know that Weber is what? Where is Weber here? kg meter square per second square ampere raised to minus 1, right? So Weber is this and current is A. So divide by A. So this becomes kg meter square per second square ampere raised to minus 1 into A raised to 1 will go up, it will become A raised to minus 1. So this is nothing but kg meter square second square A raised to minus 2. This is nothing but Henry. Here, what is Henry? Inductance. Inductance. Clear, children? Clear? Clear?
Yes, ma'am.
Yes, ma'am.
Perfect. All right. Now we will go ahead with the next one. So are you understanding what we are trying to do? Are you understanding what we are finding? So can someone tell me what we are doing? What is this all? What are we trying to do? Yes? There are certain quantities in physics, okay, and those are nothing but derived quantities. We have fundamental quantities which are independent quantities, and we have derived quantities which are derived from the fundamental quantities. So fundamental quantities have certain base units. What are base units of SI system? Right, kg, meter square, second, then what is Kelvin, right? Then we have radians, steradians. All these are nothing but base units. So derived quantities also have SI unit. Like see, induction has Henry. Henry is a SI unit. But what is its base unit? That means base unit means this Henry, I'm trying to convert it in terms of MLT, mass, length, time, and all of that. Okay, that means the base quantities, the fundamental quantities, kg, meter square, and all of that. So once I'm converting this to here, what I get? That I'm writing. So basically, I'm deriving nothing but the same unit. This is also same. If I say inductance is this one, suppose I say inductance is 20 kg meter square per second square, per ampere raised to minus 2. It means Weber per ampere only. Okay, this is same as this only. But this only I am expressing in terms of its base units. Base units means in terms of kg, meter square, second square, and ampere square. Per ampere square. Got it, children? What we are trying to do now? Yes? So all there are many now. Okay, so as in how we are doing, there are some 26 quantities that we have to derive. It's very interesting. Okay, very interesting. Initially, it's a bit difficult. What are we doing? What are we trying to do? Okay, that. But then once you're thorough with the units and all, it becomes very easy for you to derive. All right. So it's very important that you remember all these. All these quantities should be kept in your mind. Okay, so that we can derive it easily. Okay, children. So next quantity. Next is nothing but luminous flux. Next we will derive for luminous flux. Luminous flux. Okay. Now what is luminous flux? It is a perceived power of light. The perceived power of light is nothing but luminous flux. Now the total power of electromagnetic radiation is called as luminous flux. How much powerful it is. Whenever there is an electromagnetic radiation which comes, how powerful it is. Is it powerful? Yes. How powerful it is nothing but the luminous flux. Luminous means what? Brightness, right? So brightness and flux is nothing but collection of rays, or collection of something is nothing but flux. So magnetic flux means collection of magnetic lines of force. Electric flux means collection of electric, field, electric lines, we call it. Now similarly, luminous flux, collection of radiation, right? So but what? So therefore, this collection, how powerful it is nothing but luminous flux. And the luminous flux symbol, the SI unit for luminous flux is nothing but lumen. Lumen. Okay? And lumen, the symbol is nothing but Ln. The symbol for lumen is Ln. And the base unit is nothing but candela. Candela, we know candela is luminous intensity, right? How much intensity is experienced at that solid angle, and solid angle is expressed in terms of Ceridian SR. So CD by SR is nothing but the base unit for luminous. Got it? Even candela, that is luminous intensity, is also a base unit, right? Candela and solid angle, Ceridian. Luminosity in terms of candela and solid angle in terms of Ceridian. So both of these are also what? They are also base units. So we cannot further divide them. So luminous flux is nothing but how much luminosity is experienced at that solid angle. So this is some solid angle. Okay. So this is some solid angle with area. So how much power is experienced in this angle? All right. In this particular solid angle, we call it as luminous flux. And that is nothing but CD divided by S. Easy? Got it? Yes? Yes, children?
Yes, ma'am.
Okay.
Yes.
Now we will go ahead with the next one after 5 minutes. Okay, 5 minutes, we'll get back again. So children, are you understanding what I'm trying to teach? Are you understanding something? Can you all just switch on your cameras for a moment? I just want to see you. Yeah, quickly. Quickly switch on your cameras, all of you. Yes? Everybody there? Can everyone switch on your cameras for a minute, please? Daksh, Dhruv, Harshit, Prachita, Vidyut, Piyusha, Balaji. Can you all just quickly switch on your video cameras? Yes. Thank you. So are you understanding, children, what I'm trying to say? It's a bit different. I know it's a bit different because it's a new field, but still try to, understand. Okay, because if you can understand the concept, then you can derive it very easily. All right? Yes? Everybody, quickly switch on your videos. Vidyut, Dhruv, Harshit, Balaji, Bhargav. Yes, quickly, quickly. Yeah. Thank you so much, Vidyut and Prachita. What about Harshit, Dhruv? Quickly, children. Never I have forced you to switch on, but I want to know from you. That's why I'm telling you to switch on your cameras. Yes. So are you understanding what I'm trying to say, children? Are you like getting it what we are trying to do? Is there anything
Yes, ma'am.
that you're facing complications? Is there anything that you're not understanding? I want you to be honest. I want you to be honest with me. Is there something that you want again that you want me to redo it for you? Yes? So everybody is understanding what I'm trying to say?
Yes, ma'am.
Yeah? Perfect, perfect. Okay, children, thank you. Thank you so much for Vidyut and Prachita, Harshit, who switched on your camera. All right, so we'll continue with where we stopped now. All right, so the next quantity after, so we studied inductance, then we studied luminous flux. So after this is nothing but illuminance. Illuminance. Okay, we are going to study what is illuminance. Now, what is illuminance? Illuminance is nothing but the amount of luminous flux per unit area. Amount of luminous flux per unit area. Now, see, we know what is luminous flux, right? And per unit area is nothing but meter square. So, can you derive this? What is formula for luminous flux? So luminous flux, we have what? Illuminance. Illuminance is nothing but what? Amount of luminous flux per unit area. So just now we derived what is luminous flux divided by m square. What is the answer that you get? Can you quickly do it? Yes? Everybody pen on paper? Amount of luminous flux per unit area. Okay? So amount of luminous flux is given by Lm divided by unit area, that is m square. Lm is nothing but luminous flux. Okay? And divided by m square is area. So can you tell me what is the answer in terms of base units? Just now you derived for luminous, right? Luminous flux. So Lm is luminous flux divided by m square. What is the base unit that you get? Yes. Yes. Yes, children?
Candela per steradian, uh,
Correct.
meter minus 2.
Yeah. So per meter square. Very good. Very good, Prachita. So we already know that luminous flux was candela per steradian, right? Then the whole divided by meter square. So can I write this candela per steradian as CD SR raised to minus 1 divided by m square. So this will become candela steradian raised to minus 1 per meter square. M raised to minus 2. Easy? Got it now? How we are deriving? I'm so happy. At least one person did. What about others? What about others? Other children? You all understood this? How we got it?
Understood, ma'am.
Perfect. If you will give me answers no, then even I'll be motivated, okay? Or else I'll think if you'll understood or am I going very, I'm not making you understand. So that thing is there in my mind. So that's why I keep asking. Okay? Yes. So now we will go ahead with the next one, that is activity. Which activity are we talking about now? Radioactivity, right? So activity of a radionucleus or radioactive source is nothing but the number of disintegrations it has per second. Okay, number of disintegration a nucleus undergoes. So suppose this is a nucleus. When a neutron hits the nucleus, it undergoes a disintegration, right? Correct? So the number of disintegration a nucleus undergoes, activity is nothing but number of disintegration. Disintegrations the nucleus undergoes. The nucleus undergoes. Okay. The nucleus undergoes per second. Per second. That is called as activity. Okay. Or the number of unstable atomic nuclei that decay per second in a given sample. That is a textbook question. And the name, the SI unit given to activity is becquerel. Okay, becquerel. 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 Okay, and the symbol is nothing but BQ. That's all. Symbol for becquerel or activity is nothing but BQ. And the base is nothing but what? It is per second, correct? Number of disintegration and nucleus goes per second. So its base unit is S raised to minus 1. That's all. Understood, children? Clear? Clear? Yes? Yes?
Yes, ma'am.
Okay. All right. Now, did you all copy this? Copy it?
Yes, ma'am.
Okay. Okay. Now we will go ahead with the next one, that is absorbed dose or absorbed dose index. Absorbed dose or Absorbed dose index. Absorbed dose index. Now, what do you mean by absorbed dose or absorbed dose index? A dose quantity. What is a dose quantity, children? If I'm telling dose, this much dose you take. So what is this dose? It is nothing but measure of energy that is deposited in a matter by ionizing the radiation. Okay, so what happens is, best example I could give you is, what do I say? Okay, there is a matter, okay? There is a matter here, all right? And there is certain energy that is deposited in the matter, right? Some energy is there. It has some energy, correct? Now, a dose quantity is nothing but the measure of that energy that is contained or deposited in the matter. It is deposited in the matter by ionizing radiation per unit mass. So whenever there is a radiation that comes in contact with this matter, okay, the ions. So basically, the ions, it becomes into ions. It splits up into ions. The electrons, turns to be ions, right? So basically, how much that dose of radiation is induced, okay, such that it is ionized. The energy in matter is ionized. That is called as absorbed dose. Okay, a dose quantity is nothing but measure of energy deposited in a matter by ionizing radiation per second. Okay, how much how much is absorbed, how much the radiation is absorbed, such that the energy is converted into ions. That is called as the absorbed dose. Okay, and the unit is given by gray, Gray, gray. All right, the SI unit of absorbed dose is nothing but gray, and the symbol is nothing but GY. Gray. Gray is nothing but the SI unit of absorbed dose, and the symbol is GY. Okay, and gray is nothing but joule per kg. Joule per kg. Okay, now what is joule? Ethan, tell me what is joule? The base quantities for joule. Ethan Lewis. Ethan, what is base quantity for joule, Baba? Yes, Ethan, I can't hear you. What is base quantity for joule, Ethan? Harshit, what is base quantity for joule, Harshit? Harshit, what is the base quantity for joule? So many things we derive with joule, no? Joule. It's on your screen here. Joule, kg meter square per second square, right? So kg meter square per second square divided by kg. Kg cancels, so meter square per second square is the base units. Base unit. Clear? Clear, children? Clear? So here we have ended some special names. So these becomes the basis for the next quantities now. All right. So here we have ended what? Deriving some special quantities. That means derived units, right? Like magnetic flux, then absorbed index, then also what is that? Luminance flux. All this we use to derive the next set of derived units now. So these are all the bases. You need to make a chart of them. Okay. And also I have sent you just now in the group, I have sent you a chart. Okay. A chart I have sent you where all these are there. Fundamental quantities, their SI units and their base units. All three are given there. Okay. Derived units and their SI quantities in terms of base units. That is also given. So you keep these, fundamental units until here. Until here, whatever we have derived, these units you keep in mind. Very important till here. Okay. Now, next whatever we'll derive will be on basis of what we have derived before. All right. So it keeps on going. Derivation of derivation, derivation of derivation. So this should be made very strong. These are all fundamentals that we have studied till now. Okay. Make this very strong. Rest of the concepts become very easy. Now whatever we derive, it will be damn easy. Okay. Very, very easy. Only this was a bit you needed some mind, you needed to put in some mind to understand. But henceforth, whatever we derive now, everything fatafat you'll understand. Okay. Now we will go ahead with the next set of units. All right. Okay, now we will go ahead with some SI derived units expressed by means of SI units. So we are going to derive some SI derived units. Derived units, okay, by what we are going to derive? By the means of SI units. But whatever we have derived so far, all these units we have derived now, right? So using all of these, we are going to derive the next set of units now. Okay, so let's start. The first one that we are going to derive by using the basic formula so far is nothing but magnetic moment. Magnetic moment. Yes. So what is magnetic moment, children? Magnetic moment is nothing but the magnetic strength and orientation of a magnet or other object that produces a magnetic field. What do you mean by all this? Now, all right, the magnetic strength and orientation of a magnet. Now, suppose there is a conductor, okay, electric field passes through this conductor. The magnetic field is produced around this conductor, right? Now, the magnetic strength, how strong is this magnetic field and the orientation of the magnet? How is the conductor acts like a magnet, right? So, how is it oriented? And or the other object that produces a magnet, is there any other object which produces a magnetic field? Example, loops of electric current. Now, there are loops of electric current, right? So, one loop of electric current. Suppose there's one loop of electric current, okay? One loop of electric current, permanent magnets or elementary particles or various molecules and astronomical objects all have something called as magnetic moment in them. What is this magnetic moment? The magnetic strength and the orientation of the magnet. How much strength it has, right? That particular conductor, how strong it is to conduct a magnetic field around it. So that is called as magnetic moment. All right, and magnetic moment, the SI unit of magnetic moment is nothing but joule per Tesla. Joule, joule per Tesla. Joule per Tesla. What is magnetic moment? Please write down the magnetic strength. The magnetic strength. The magnetic strength and orientation of a magnet. And orientation of a magnet, okay, or any object. It may be or any object that produces a magnetic field, which produces a magnetic field. That is called as magnetic moment. Okay, and it is expressed in terms of joule per Tesla. Joule per Tesla. So let us express the SI unit joule per Tesla in terms of base units. Okay. So expression in terms of base units. Expression in terms of base unit. Okay. So now joule per Tesla. What is joule? What is joule? Yes. Energy is nothing but joule. Energy in a particular direction. We call it as a joule. So what is energy here? kg meter square per second square divided by Tesla is what, children? The magnetic field, right? The magnetic field experienced is nothing but Tesla. So magnetic field is given by kg per second square per ampere, right? We have already derived the units for joule and Tesla. Now, kg gets cancelled, s square gets cancelled. Remaining is m square divided by per ampere. So this is nothing but meter square ampere or ampere meter square. Easy? Got it? Got it how we derived it? Yeah? So these quantities, whatever we studied so far, become the base now. You have to have it on the tip of your tongue. What is the base unit for joule? What is the base unit for Tesla? What is the base unit for, volt, current, electricity, all, whatever we have studied so far. All right. So using them, we are deriving the next set of derived units. Got it, children? Yes? Magnetic moment. So can somebody tell me what is magnetic moment? Can Varish tell me what is magnetic moment? Yes, Varish? Yes, Varish? Somebody in the house here? Somebody? What is magnetic moment, children? Magnetic moment. Do you want me to redo the concept? Or will you tell me what it is? Yes? What do I understand? If you are quiet, I can't understand anything. You should say, ma'am, redo, or ma'am, yes, we have understood. Yes. Magnetic moment, children?
The magnetic strength which produces the magnetic field.
Correct. Very
Energy by
correct. Yes. So how did I derive this, Baba? How did I derive magnetic moment? How did I derive?
Joule by Tesla.
Correct. What is joule? Joule we have already derived. That is nothing but kg meter squared per second square divided by Tesla. We have already derived. That is kg per second square ampere raised to -1. Right, children? Yes. Understood now? Thank you.
Yes, ma'am.
Prachita. At least Prachita and Vidyu are telling. Then only I'm understanding. Or else I'm not understanding if you are understanding or no. Please tell me. All right. Okay. Now we will go ahead with the next set, that is nothing but dipole moment. Okay? Dipole moment. Next quantity called as dipole moment. What is dipole moment? When there is a separation of positive and negative charges, the bond is established, right? Example, it can occur between two ions as ionic bond, or it can occur between two atoms as a covalent bond. Like what? Now suppose there is this atom A and there is this atom B. Okay? It has 1, 2, 3, 4, 5, 6. One atom is left out, it does not have a pair. Similarly, this is one more atom. 1, 2, 3, 4, 5, 6. One more, one more electron is left out. It does not have a pair. Okay, so it has 1 electron, 2 electron, 3 electron, 4 electron, 5, 6 electrons. Here also it has 1, 2, 3, 4, 5, 6 electrons. Seventh electron does not have a pair. So what happens? Now, when there is a separation of positive and negative charges, the one bond is established between them. Okay, so they come together. This and this come together. There is again 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 7. Got it? This bond is established between atom A and atom B. That is nothing but dipole moment. Okay, so there's a link formed between an electrostatic attraction between two opposite ions. It may be positive or negative, and positive and negative. Okay, it should be positive and negative. So whenever there is two positive ions or of opposite charges, there is some attraction that is experienced, right? So that is called as dipole moment. Okay, it can exist between ions as ionic bond, or it can exist between what is that, covalent bond also. Okay, that means sharing of electron pairs between the atoms. So here there's a covalent bond that is established between them, right? So why? Because electron pairs are shared between both the atom A and atom B. So that's why we call this as a covalent bond. And why is this bond formed? Because of the dipole moment. Dipole moment is nothing but whenever there is a separation between two atoms, okay, now the one bond is established. There's an attraction felt between two different pairs of electrons of two different atoms. So that is nothing but dipole moment. All right? Yes. And the unit is nothing but, unit of dipole moment is Coulomb meter. Coulomb meter. Coulomb meter. Okay. Now what is coulomb here? Ampere second. Sorry, ampere second. And meter is M. Right? So what is the unit here? Ampere second meter. That's all. Is the unit for dipole moment. Clear, children? Clear? So can somebody tell me what is
Excuse me,
dipole
ma'am.
moment?
Ma'am, I didn't get the dipole moment properly, ma'am.
Okay. Now there are two atoms here. Okay. Atom number A, atom number B. Okay. Now what happens is whenever there is separation of positive or negative charges, okay, see there is certain attraction that is experienced, right, between certain positive and negative charges. Now when there are two atoms, okay, in a molecule, now suppose it has pair. Now always electrons are experienced in terms of pairs. You will learn that in your chemistry classes, the energy levels and all of that, right? So there is electron, electron, two. See, there are pairs, right? Everywhere there are pairs, pairs, pairs. Here also there is pair. Here also there is a pair, and here also there is a pair. Now one electron is left like that. One electron is left like that. So this electron gets attracted to this. This electron gets attracted to this. So it forms a bond called as the covalent bond. Alright. So here, normal what this atom A and atom B is, right? So it has two. It has two here, two here. It has two here, it has two here. Here also it has two. Here also it has two. Here also it has two. Now this is one and this is one. Together they form two. So this is a bond that is established between them. That is nothing but for dipole moment. The bond established is due to the dipole moment. What is the dipole moment? A bond that is established whenever there is separation. Okay, that is called as dipole moment. One bond.
Okay, ma'am.
Okay, all right. And that is nothing but Coulomb meter. The unit name that we call is nothing but Coulomb, Coulomb meter. We know that SI unit of Coulomb is what? Ampere second, and meter as it is. So ASM. ASM is nothing but base unit for dipole moment. Got it, children? Got it?
Yes, ma'am.
Okay. Now we will go ahead with the next one, that is dynamic viscosity. Dynamic viscosity. What is viscosity? What is viscosity?
Ma'am, the flow of a liquid, like how fast it flows, or like the thickness, the
Resistance to the
density.
flow of liquid. That is called as viscosity. Yes. So now dynamic viscosity is nothing but resistance to the movement of one layer of fluid over the other layer. So there is one fluid that is flowing this way, and there's one more type of fluid which is flowing this way. So this fluid resists the flow of this fluid. So that is called as dynamic viscosity. One fluid resisting the flow of the other fluid. Okay. So that is called as what, children? Dynamic viscosity. Resistance experienced by fluids which are flowing in two different directions. That is called as dynamic viscosity. Okay, and dynamic viscosity is nothing but the name given to it is Pascal second. Pascal second. Okay, Pascal second. So, Pascal second, or also we call it as Newton. They also call it as Newton second per square meter. Newton second per square meter. So Newton second per meter square. Alright, children? Newton second per meter square. Or it can also be written as Pascal second. PAS. Pascal is nothing but unit of pressure and second. Got it? Easy? Yes? Yes? Yes or no?
Yes, ma'am.
Yes, ma'am.
Please reply, or else I will not understand. Okay. All right. Okay, good. Next, after knowing about dynamic viscosity, let's go ahead with the next one, that is torque. Torque or couple. torque or couple or moment of force. All these have the same unit, moment of force. What is torque, children? We have studied in the first chapter what was torque, right? What is torque? Torque. Anyone? What is torque?
The force that acts perpendicular.
Yes, to the direction of motion, right? Now suppose example was, see, I'll tell you very simple. Okay. Now there is a rotational motion this side. Okay. There is opening and closing of a door, and the door is rotating to and fro. So there is a rotational motion this side, and perpendicular to that motion, which acts, is nothing but torque. Correct? There's a torque which acts. The force that makes it happen, that is nothing but torque. If torque is absent, then it keeps on going. There's no change in direction. Because there's torque acting, that's why from to it goes fro it goes to. That is why that is nothing but torque. The perpendicular force that acts between a motion, between a object which is rotating, that is called as torque. Now, torque is nothing but a force applied to the object at a point away from the point of rotation. So suppose what happens is, this is an object, okay? Suppose this is an object and this is the point of rotation. Point of rotation. So this point, if I open it, the door will go like this, the door will come like this. So this is the point of rotation here. It goes this way. Again, it goes this way, it goes this way, it goes this way. This is the point of rotation. Okay? Now, there is a force which acts perpendicular. There's a force which acts perpendicular to this. Okay? The force which acts perpendicular, that is called as torque. Suppose this is at a distance d and force is given by S. So, torque is nothing but torque. 2 is equal to F into d. Force experienced by the object and the distance of it, right? From the point of rotation. That is nothing but torque. Okay, what is torque? The force, the perpendicular force which acts and the distance from the point of rotation and the distance of that object. Okay, the total length of that object. So torque is equal to F into D. Force into D. Now, so therefore, what is the unit for this, children? Torque causes an angular acceleration. Because there is a torque, that is why we see that the object which is undergoing a torque has an angular acceleration to it. So therefore, okay, so we know that force is nothing but Newton and distance is nothing but meter. So therefore, torque is equal to Newton meter. Easy? Yes? Torque is equal to Newton meter. Now, what is Newton? What is Newton again? Yes? The base quantity for Newton is?
kg meter per second squared.
Kg meter per second square. Thank you, Prachita. And multiply it with meter. Newton meter, no? So kg meter per second square into meter will give me kg meter square per second square. Got it, children? So this is the base unit for Newton meter. Yes? Understood? Easy? Easy peasy?
Yes, ma'am.
Perfect. Now we will go ahead to the next one, that is surface tension. Surface tension. See, I'm doing it slow because these are very important quantities. Okay, I hope you all are understanding. This is basic for the coming physics. All basic things. Now, surface tension. Okay. What is surface tension? Tell me in a funny way. What is surface tension? There is a surface, okay? It has too much of attraction pull towards it, towards the surface, and that is why some tension is felt in that surface, right? If there's so much of pressure experienced by the same surface, what will happen? It will become tension. You have some tension, right? So therefore, that is called a surface tension, basically, in normal terms if I talk. Or I can say the attraction of particles in the surface layer. So suppose there is a layer here, surface layer. There are particles here, right? There are particles in the surface. There is some attraction that is experienced between the particles in the surface, okay? And it tends to minimize the surface area. Because of this attraction, this wide will become this much. There's a reduction in size of this surface. Correct? Yes? So the tension experienced at the surface of the liquid, there is this tension of attraction. The particles are only getting attracted, the surface area is becoming small. So that is called as surface tension. The tension experienced by the surface, each other. Alright, that is called as surface tension. And see, there is a certain force involved in that particular area. So the SI unit is given by force experienced into that particular area, or at that particular meter, we say. So F into M, or we call it as force is nothing but Newton per meter, right? Newton per meter. Force experienced in that particular area, right? Or we call it as force experience in that particular area, or it is nothing but Newton per meter. Now, what is again Newton's formula? Kg meter per second square into per meter. So this will become kg m raised to 1, m raised to minus 1. M raised to 1 into m raised to minus 1. It becomes m raised to 1 minus 1, m raised to 0, which is nothing but 1. So m will get cancelled and only s square will remain. Yes, children, got it? Yes? Kg per second.
Yes, ma'am.
So what is surface tension? What is surface tension? Bob raises so much still. What is surface tension, children? At a surface, there are particles and they experience a force of attraction. And the surface decreases once the particles undergo attraction. The tension produced at the surface because of the attracting particles is called as surface tension. It is given by force in that particular area, right? So force per meter. Force is nothing but Newton. Newton per meter. Newton is nothing but kg meter per second square per meter. That's it. Clear? All right. The next quantity that we will study now is power density. Power density. Power density or irradiance. Irradiance or heat flux density. Heat flux density. Okay. So what is power density? It is the amount of power per unit volume. All right. Amount of power experienced per unit volume is power density. How much power is there in that volume? That is called as power density. And the name given to it is watt per square meter. Watt per square meter. Okay. Therefore, watt is nothing but joule per second, right? Divided by meter square. So therefore, the answer is joule per second meter raised to minus. Got it, children? Yes? Yes? Watt.
Yes, ma'am.
Per means divided by square meter, meter square. Perfect. Next quantity that we will study is heat capacity or entropy. Heat capacity or entropy. Okay? Heat capacity or entropy. Now, what is heat capacity or entropy? Now, suppose there is a, suppose there is some object. It has particles which are very far from each other. That is called as randomness. The particles are randomly distributed. Then again, after some time, the particles come little closer. After some time, the particles are very closer. After some time, the particles go together. Right? So this is nothing but entropy. The degree of randomness, how far the particles are, right? That is called as entropy. All right, children. So therefore, entropy is a measurement of degree of randomness of energy in a system, right? How randomly the energy is distributed in a system. That is called as Entropy. Lower the entropy, more ordered and less random it is. See, lower the entropy, here entropy is more. Here entropy is less, right? Entropy is less here. Why it is less? Because randomness is not there only. It is all together. Entropy is nothing but the amount of randomness. So this is random, right? There's a a huge difference in the particles. So this is called as entropy. More the randomness, more the entropy. Less the randomness, less the entropy. Okay. Example is gallon of gas has entropy. It has a lot of distribution of energy in a gas. Then we have sunlight also. Sunlight has very low entropy. Correct. So therefore, entropy is expressed as joule per Kelvin. Joule, joule per Kelvin. Joule per Kelvin. J divided by K. What is joule? Joule is nothing but kg meter square per second square divided by Kelvin is what, children? What is Kelvin? Kelvin is Kelvin only because it's the base unit already, right? We do not have any further derivative of it because this is a base unit for temperature when we were studying 7 fundamental SI units. So therefore, the unit will become kg meter square per second square per Kelvin. Got it? So we'll stop here. Tomorrow we'll continue with the next specific heat capacity, energy capacity and all of that. Any doubts still here? Any doubts what we've studied so far? I think still one more class we'll finish. One more class. Very little is there. Understood how we are trying to find it? Yes?